very pleased to welcome you all here. Many people I know, but a few I don't. I'm Bartosh. I'm Director of the Syracuse Center of Excellence, the New York State Center of Excellence in Environmental and Energy Systems. And we have a partner program. Our partners support a monthly series of research and technology forums. And this is our May program. Usually we do it on the third Tuesday. So we're so excited about this topic, we just couldn't wait for the third Tuesday. So we're doing it today. Our next RMT forum is on the third Tuesday in June 16th. It'll be on the new well building standard, and we encourage everyone to look for that announcement and mark your calendars. My pleasure now to introduce Dr. Chetna Chinese. Chetna is a research fellow at Syracuse COE, and she's going to moderate this RMT forum. Chetna.
Thank you all for joining us for our RMT forum on environmentally responsive architecture. And we're going to have 3 presentations. Bess Krietemeyer is going to talk about interactive simulations for high-performance building design. Brandon Andow is going to talk about materials research and the simulation of thin films on some other materials for dynamic facades. And then Bartosh is going to talk about some integrative and immersive media that all blends into this environmentally responsive architecture. So first up is going to be Bess Krietemeyer. Bess is an assistant professor at Syracuse University School of Architecture. She teaches studio and technical courses emphasizing environmental performance within architectural design. Her research focuses on the intersection of emerging materials technologies, human interaction, and immersive computational simulations for design of sustainable built environment. It's a mouthful, but I think her presentation will show you what's happening, and we'll also have the opportunity to just tour a lab upstairs after the presentation. Dr. Krietemeyer received her Ph.D. in Architectural Sciences from Rensselaer Polytechnic Institute's Center for Architecture Science and Ecology, also known as CASE. And she's practiced with Wilbrano Cherevara Architects and with CASE and Skidmore, Owens, and Merrill on international projects that integrate next generation building technologies. So it's a pleasure to welcome Bess. Thank you.
Thanks, Chetna. And thanks, everyone, for coming today, this afternoon. I think it's a good time at the end of the semester. Hopefully everyone hasn't left campus just yet. But today, what I'd like to talk about, and actually in the context of these 3 presentations, which is really exciting for me because both Amber and Brandon are collaborators of mine, both from several years at CASE and also kind of ongoing research. And I think the exciting thing that we're going to try and tie together here is how the computational and the material experiments are interrelated with each other at multiple scales. So I'm going to focus today on some ongoing research that's in collaboration between Syracuse University, School of Architecture, our collaborators Norflux, the Syracuse Center of Excellence, and RPI Center for Architecture Science and Ecology, which is also known as CASE. And specifically, I'll focus on the development of computational design tools for integrating human interaction into the development of responsive facade systems. And if we have time at the end, which I hope we will, we can go upstairs into the lab and actually interact with some of the things that I'll talk about today. So in the context of high-performance building skins, we have a lot of new kind of nano to micro material innovations that are really starting to change our expectations of building envelope performance towards systems that can respond to occupants' variable preferences for views, for control, for privacy, for comfort. And these systems can still meet the energy demands of buildings. And there's a real growing desire to integrate higher levels of user control with these dynamic facade systems that are typically optimized for energy performance alone. So this added desire then places an added challenge to the current methods that we normally use for measuring building envelope performance. especially since these methods tend to kind of prioritize or focus on meeting quantitative energy benchmarks. So it becomes a little bit trickier when we start to integrate patterns of user behavior when we're trying to predict energy use. And we have many types of building simulation tools that are really useful for predicting a facade's daylighting or its solar control performance, but they're also limited in terms of their ability to simulate material complexity, to provide a kind of real-time visual and analytical feedback, and also in simulating occupant behavior. And the research we have out there shows enormous potential for these dynamic facade systems, things like electrochromic windows, which we have right down the hall on the 3rd floor. But a lot of this research tends to focus on energy efficiency while kind of postponing human factors issues. So there's often a separation between the analysis of energy testing, the analysis of energy performance testing from the human factors testing when we're evaluating a new facade system's responsive behavior. We also have incredible facilities like LVNL's Flex Lab, which it's a great resource for testing advanced building systems. You can get measurable feedback on the energy impacts and environmental comfort, and it starts to incorporate users in a really important way. The only challenge, one of the biggest challenges with these facilities is that it does require us to build full-scale physical prototypes of these systems, and usually multiple prototypes if you want to test multiple iterations of them. That can be pretty costly to build. So in addressing some of these kind of technical and social challenges, our research focuses on developing a computational framework for examining the relationship between human interaction with these new facade systems and really trying to understand the impacts on the energy performance of the building and really also on architectural design. So in doing so, we're constructing these augmented reality simulations that are based on real physical material experiments that are in the early phases of prototyping. So the idea is that by testing these new material systems in the early prototyping phase, for both energy performance and for user control, the goal is to kind of avoid reinscribing this divide that currently exists between these two kind of quantitative and qualitative criteria. So one of the systems that I spent many years working on, you'll hear more about it from Brandon Andow, we're using this system as a primary test bed for a lot of the simulation work. And this system is called the Electroactive Dynamic Display System, or EDDS. It's a dynamic facade technology that's been developed at RPI's CASE. And it actually embeds electropolymeric materials within the surfaces, interior surfaces of an insulated glazing unit for a very highly responsive condition across the building facade. So each polymeric micromuscle acts like a little pixel in a display screen. So we can have a lot of opportunities for user control over both the environmental effects, but also the kind of visual patterning effects. So this particular assembly relies on an electric current to alter the mechanical behaviors of individual metallized polymers within an ITO matrix. And when combined into multiple layers for a double or a triple pane system, glazing system, the whole system can be programmed to geometrically track the incoming solar radiation to either block, to absorb, to diffuse light in the visible or the infrared spectrum, while still maintaining views past the open pixels. So at the same time, the EDDS could be programmed for interior applications or customized for individual preferences along the facade for things like privacy or other kinds of media or information display. It can also track multiple users within a space, while at the same time still adjusting to the changing exterior environmental conditions. So one of our big questions was, if we have so much control over what the facade looks like from a user perspective, what are the effects of this on the overall energy performance of the facade and of the building? And how do we design these adaptive materials to negotiate between the environmental and the occupant demands at the same time? So how can a simulation tool better integrate these criteria? So we started developing a simulation tool. These are some images from an earlier iteration of this simulated environment for programming the EDDS. And this was installed at Rensselaer. So in this setup, we have a kind of semi-immersive projection environment that's simulating the dynamic patterning of the EDDS, and it's visualizing the daylighting effects in real time. So the idea of a kind of semi-projected, large-scale visualization environment was really crucial to the research because it allowed us to test the environmental effects of a new material system that wasn't physically scalable at this point in time. There are, of course, limitations to the use of projection, and along with the need to incorporate multiple users within the simulated environment. So we want to be able to tie in multi-user control to algorithms that help us understand the whole building energy impacts. So this initial setup also only supported single-person tracking. And we wanted to explore how systems like EDDS could negotiate its response to multiple users and then understand its energy impacts. So in order to do that, we've been developing the simulation environment to support multi-user interactions with both what we call kind of augmented and virtual or immersive virtual reality environments. So the next generation of this simulated environment is being developed through the Interactive Design and Visualization Lab, which is located right up on the 5th floor here at the COE. So here the interactive simulations are being improved for their speed and their accuracy relative to the environmental and human response. We're starting to incorporate gestural interactions and other kinds of applications for remote control. So in the simulated environment, you can use multiple sensors to actually indicate where people are, not just relative to their proximity to the facade. So the idea is we can test multiple material prototypes. We can test a range of complex geometries and different patterns, and then link this simulation with commercially available energy analysis software, where we can start to test new methods for human interaction. We can design these new methods, record them, and analyze them based on a range of user inputs. And we can experience not only the interior conditions of the room, but also the exterior conditions as well. And basically plug in any 3D model, any geometry, or any kind of facade system that you might want to simulate. So again, it's a framework. We're using the EDDS as an initial test bed, but the idea is we can swap out different types of systems, whether it's electrochromic windows or maybe systems that are being developed in other areas in campus that, again, haven't been able to scale up physically just yet. So these are just a couple of views of the simulation, a couple of exterior views, where you can see the simulation is tracking one person's perspective on the left, and on the right would be our own perspective as we're kind of moving back and forth along the screen. So we're looking at basically a big 2D simulated screen, which we can see upstairs. We're developing techniques for data collection, where we can document and record gestural interactions so we can start to analyze the tendencies to which people might modify or adapt their own response based on the way that the facade is responding. So there might be a kind of learned behavior between the user and the facade. And again, the big idea being that we can understand how these systems can negotiate between potential conflicts between groups of users in a space, and also conflicts with building demands. And receive real-time feedback at different scales. So at one scale, we're trying to understand the glazing system's ability to mediate solar heat gain and daylight. And you can see that kind of shown in these pop-up data panels. Other methods for energy feedback incorporate daylighting analysis grids into the semi-immersive environment, where the user can interact with the facade and still receive real-time feedback on the illuminance levels that are now being projected onto the floor. But again, what are the whole building energy impacts of this, which is still a kind of single-zone human facade interaction? And how can we design the algorithms, the control algorithms for these material systems to reduce the building's energy loads and also accommodate the multiple occupant desires for controlling views, privacy, comfort, patterning. So we're now linking the interactive simulations to whole building energy analysis tools like NRT+, so we can understand the environmental and the visual impacts simultaneously of this kind of live interaction at a larger building scale. And we're starting to examine ways where the system might have to compensate in order to maintain a desired solar control or a specific daylight level in the interior, where it might have to adjust its pattern densities depending on how a person might kind of interrupt its default solar tracking state. And then integrating this information again to Energy+ whole building energy modeler. And there are still a lot of assumptions with within this workflow, such as how we might translate a complex material geometry to a value that Energy+ can actually understand, along with the need to calibrate more precise material properties of the physical prototypes to these digital simulations. But the framework is in place for this whole building analysis to consider live human interaction as valuable input in the design and development process, where we can understand both the environmental and the architectural implications of interaction at multiple scales. And it's really important in this case that we're able to expose these methods to a wider audience and in different settings to get a range of user input. And again, develop these simulations in parallel with the physical prototypes. And there are a lot of challenges we're still working through in terms of the kind of mobility of the simulations or the need to support multi-user tracking. And we're working on these through the research that's incorporating virtual reality tools like the Oculus Rift head-mounted display. So with tools like the Rift, we can simultaneously design and interact with a dynamic facade in virtual space. We've kind of moved from augmented reality to immersive reality, and still have the ability to modify its behaviors in real time, and still have the ability to understand the energy implications in real time. So we're pushing these boundaries to the whole building and even the urban scales, where we can visualize both dynamic systems in action, but also visualize the kind of ambient energy flows that are happening at these multiple scales. And we'll hear a little bit more about that from Amber's presentation in terms of these other multi-scalar virtual reality applications. So this combination of the hybrid reality simulations offers a lot of exciting opportunities for the testing process, but also the architectural design process, where people could actually collaborate remotely on the same interactive virtual model, which starts to provide a common visual language where we can receive real-time energy feedback on design decisions. So this starts to enable an interdisciplinary dialogue between the lab-scale materials research and these interactive spaces that can visualize and test their scalability within a range of environments and applications. So one example of this is, as a result of the simulation work with the EDS, a broader set of architectural criteria for both environmental and user-driven performance is pushing for greater adaptability of these materials at not just the micro, but now the nano scale. So, and we'll hear more about that from Brandon's presentation, but again, there's a stronger emphasis now on criteria for user control, what the architectural implications are in terms of aesthetics and appearance. So all of these things start to become important parts of these design feedback loops. So our goal is to continue developing these simulations along the multi-scalar physical prototypes for new advanced building materials and systems. And the idea, again, is by simulating the behavior of intelligent materials at larger, full scales for human factors testing, and the feedback that we get from this computational framework can actually start to inform the engineering and the material prototyping of these systems in their early development phase. Thank you.
bringing up Brandon's presentation. Yeah, that looks good. I'll introduce Brandon Andow. Brandon is a Ph.D. candidate at RPI's Center for Architectural Science and Ecology, CASE. He is researching multifunctional dynamic glazing materials and solar responsive facade systems. The aim there is improving energy efficiency in buildings while also improving indoor environmental quality. Prior to his graduate research, Brandon worked in architecture for 6 years in New York City with a year-long hiatus to work in Antarctica, repairing buildings at the McMurdo station. He received his MS in Architectural Science from Rensselaer in 2010 and his BA in Architecture, Bachelor's in Architecture from the Rhode Island School of Design in 2004. So, Brandon.
Thank you very much. So I'm just going to talk briefly, continue this discussion with some recent materials research that we're looking at as far as dynamic transmittance modulation for windows, and then I'll briefly talk about how some methods that we're using, I would say, slightly more conventional in the sense that they're not real time, but advanced modeling methods in order to scale up the material properties into whole building energy modeling and visual comfort modeling. So we know that windows have a significant impact on building energy use.
Can we take pictures, or is that down low?
I think it's going to be recorded. Yeah,
Recorded, it's up to you if you
you're welcome to take photos. So we know that windows have a significant impact on building energy use. So of the major loads on a building, the lighting, cooling, and heating loads, windows can affect up to 43% of that energy use. But that challenge, that realizing those potential savings is challenged by a number of sort of complicated intricacies of the daylighting problem. So when we have highly glazed envelopes, we have often conflicting requirements that are dynamically changing. We need to mitigate or promote the transmission of light for daylighting or artificial lighting load reduction. We need to control the transmission or absorption of heat for thermal comfort and thermal load reduction. We need to manage the direction and intensity of light for visual comfort, glare avoidance, and productivity. We need to promote the proper visible spectrum distribution at the appropriate time of day for human physiology and circadian entrainment. We need to simultaneously achieve all of the above while co-managing privacy with views to the exterior and serving as the primary design element of the architecture. The facade is the primary design element that we have to work with. And then additionally, for net zero energy buildings, any incident solar energy that's not directly used as daylighting needs to be converted into something useful. So that's the overarching goals that Bess mentioned. We took a look at performance criteria for dynamic windows, and this is something we've sort of referred to as dynamic facades as a slightly larger umbrella. How do facades manage the energy flows at a building envelope in order to take care of all the needs of occupants in the building? So that's a sort of complicated set of requirements. Now there are plenty of dynamic window technologies that are out there that exist in different levels of development, and we're familiar with some of them. Electrochromics, so I'll go down the line, sorry, they're all abbreviated. Electrochromics, suspended particle devices, liquid crystal devices, photochromics, thermochromics, gasochromics, which are largely in the lab. There's some recent developments on microbrines, and we have the EDDS system up there as well. But given the complex set of performance criteria, particularly when it comes to meeting human comfort requirements, human glare avoidance, and interaction with the facade, we actually see that not a lot of the systems are able to manage all of these different design requirements together. And the leading technology, electrochromics, which we've seen in the building, it still struggles with issues of color neutrality, slow switching time, and the ability to control glare. So electrochromics have to go down to a very, since it's a specularly tinting film, they have to go down to a very dark state in order to control for glare when there's sun on the window. So for this reason, we want to look at what are the possibilities for new material developments for dynamic glazing, for modulating the light that comes, light and heat that comes into the window. So we're looking at, it looks like the title's a little cut off, sorry about that, but we're looking at graphene oxide thin films, which are very mechanically robust. And when we wrinkle, we can dynamically wrinkle these films and create crumpled structures, which and result in light trapping and light scattering structures. So here, just initial studies where we're uniaxially stretching this substrate, and when we deposit the graphene oxide thin film, we're talking about 20 to 80 nanometer thin films. When we release that strain, it crumples the structure. And when we can dynamically strain and unstrain that substrate in order to control the topology of that, the topography of that structure. When we do it uniaxially, when we release it, it obviously creates tears in the transverse direction as the material expands. But as we move to biaxially straining the films, we get a very nice, dense, wrinkled structure in this very mechanically robust thin film. And so what that allows us to do is go from a flat film up into a crumpled structure, which creates light scattering and light trapping. Again, these are a very small, couple microns in terms of what the full dimensions are of this. So there you can see a lab scale prototype, about a centimeter square on the top, of the film being strained, going from an opaque state to a transparent state on the right. And then there's a microscope image of that film as it goes from a dark state into a transparent state. And we can, the last two of the sort of pinkish images on the right, we're actually overstraining the film, which can, if we need to, we can start putting more transparent films and changing the dynamic range of that film. So the direct neural transmission here on the lower left, we can actually achieve, with some very high strains, we can achieve pretty wide visible transmission range from 0.09 to 0.87. And then solar transmission range is a little bit smaller, but from 0.18 to 0.9. We cycle the film over hundreds of cycles. We've actually gone up to 500 cycles, and we see only minimal degradation of the transmitting properties as we cycle the films. So we are, this is a delaminated buckling structure. So these, we are peeling blisters off of the film and laying them back out flat. So we definitely want to test how well that cycles over many cycles over time as the window needs to change a lot. So that's cursory. Obviously, we need to get up more to like 10 to the 5 cycles for a viable product, but we see good resistance to degradation so far. And so we went through a lot of modeling, and actually Bess showed more of the finite element modeling that was done in one of her slides, but we come up with some just analysis of how the folds mechanically form when we put the film under strain. And so on the top we have AFM images of various pre-strains of the films, and then the red line is the theoretical prediction, and we seem to fit pretty closely. The effect of film thickness on the wrinkling is theoretically doesn't have as much of an effect on the wrinkling. And this is just simply because the degree of wrinkling, which is plotted on the left, is a function of the amplitude and the periodicity of the wrinkles. And so as you get thicker films, you actually just get higher wrinkles with the lower periodicity, so it sort of cancels out. But we're basically looking for what are the ways in which we can control the optical tuning properties of the film. And then lastly, of course, we put it in, this is just an integrating sphere setup where we want to look at the total transmission and reflection of the films. And here, so we see a number of different film thicknesses at the bottom, as well as multi-layer stacks of films. And as we strain and release those dynamically in the integrating sphere, we can start to move around and modify what our transmission range is for the films. So we have a fair amount of movement that we can do, and then again, as I mentioned, we can sort of overstrain the films when we do need to make them more transparent. And then so these are summing up the sort of the transmittance ranges that we were able to achieve. And with varying thicknesses and multiple layers, we can start to get a range that's competitive with what we need to be for deploying into a building on the far right side there. And that little dotted line, again, is overstraining the film. We can start to increase the transparency at the high end if we need to. So that's just a brief update on some materials developments. And then we want to sort of project into the future or scale up what the effects of material properties are that we're investigating, and how that affects the visual comfort and whole building energy use. So you can imagine, again, a sort of pixelated system. You imagine the wrinkled structures would stretch and close in order to wrinkle the graphene oxide film, and we could put it on surface 2 and surface 3 of an IGU, similar conceptually to the EDDS work. So it's a model that we're using with similar assumptions to model EDDS, as well as a projected version of a graphene oxide device. So here, just describing what solar tracking looks like with that. If we deploy, we can turn certain pixels on and off, and we can start to follow the direct beam of the sun. And this is very important for visual comfort, as we, if we start to block just the direct beam and allow diffuse light to scatter through the window, we have a much lower contrast that comes through into the space and is able to better control for glare. And then that sort of coupled with the scattering properties of the film, we would anticipate a much better visual comfort performance from these films versus the specularly tinting films. So we start to, this is just a map of how do we go about modeling this. And again, I sort of call this conventional. It's using some of the most sort of state-of-the-art modeling techniques for modeling daylighting, and we're coupling radiance 3 and 5 phase methods, which are these are basically annual methods for doing daylight at an hourly time step. So we're going to make renderings at 8,760 renderings in order to fully characterize this sort of above and beyond what most daylighting analysis is. So we're using these new tools in radiance, which employ the bidirectional scattering distribution functions as a way of characterizing how light moves through complex systems, meaning if light comes in at one angle, it scatters in this way. If light comes in at another angle, it scatters in a different way. And so when we model that, we have to model all those different angles and different scattering on the inside. So we couple that then with Energy Plus and do an annual hourly time step. So it's a little bit of a mosaic. Currently, there's other groups who are working to automate this. I think if you want this to be more streamlined, look at the Open Studio developments coming out of NREL, excuse me. Open Studio, where they're coupling the radiance 3 and 5 phase methods to Energy Plus. Here we did it a little bit more manually, as those aren't available just yet. So we have an optically complex system with these 2 layers. So when light comes through, it's going to bounce between the 2 layers and transmit and reflect. And it's going to vary depending on what angle it's coming in at the window. So that gives us what's termed a complex fenestration system. And so in order to describe that, so here we have a number of states that we're simulating of the EBS system or the hypothetical graphene oxide system, where you have staggered pixels on 2 different surfaces. And we're going to for each of those different states that we simulate, we're going to develop this matrix, a scattering matrix that describes at an incidence angle what the light comes through. We take these and we're using the 3-phase method, which is basically splitting the measurements that you need to do for daylighting into a lot of pre-calculation steps. So you're going to take the sky dome in radiance, and you're going to measure, or you're going to pre-calculate what the factors are for all of that light hitting your facade. And then you're going to use the scattering, the BSDF, the scattering matrix, as your window layer, and that's going to tell you at what incidence angle the light comes out. And then you're going to use another matrix inside, which tells you when light comes out this direction, it scatters in the room in this way. So what that does, you pre-calculate a lot of steps, and you can just swap out the window layers with each of these previous different states of the glazing system. So it allows you to simulate the dynamic properties of the complex fenestration system. And the end result is you get an entire hourly annual series of renderings fully characterizing the daylight in space. And so at the top there, we have a familiar 24 by 365 annual plot, basically of the illuminance in the space for an EDS system. The columns that are pulled out would be each day for the solstices and equinoxes. And then 9, 12, and 3 o'clock are further enlarged, and you can see the renderings at each of those different time steps. So we use this, we couple it again with the sort of mosaic of simulation methods. We then tie it to Energy Plus, and we feed Energy Plus with the daylighting information that we're getting, the light levels that we're getting from our detailed radiance renderings. And we end up with whole building energy modeling of the complex fenestration system, which is changing states every hour. Again, luminance, annual luminance plots at the top, the green and yellow and red are glare. So now that we have an entire annual hourly series of renderings, we can do detailed glare analysis on it as well using daylight glare probability methods, eval glare subroutine. So then we can take all those renderings and run all of those through eval glare, and we can get the daylight glare probability as well. And then again, looking at this, just looking at our major loads, lighting, cooling, and heating there are then plotted as some of those thin bars underneath. So we are able to then couple detailed daylighting analysis with the whole building energy modeling. And some of the new bidirectional scattering distribution tools allow us to take material properties out of the lab and plug them in and simulate how they would operate in window, simulate them with LBNL's window program at the glazing unit scale, build that up with glass layers, put that into an Energy Plus model and dynamically control the states of the glazing. Quick run through.
Thank you.
Amber Bartosh. Amber's going to take a quick computer change over here. Amber is an architect and interior designer. She is LEED accredited and has completed both gold and silver level LEED projects and served as a project manager for Emergent Wixom LLC, an internationally recognized architectural practice focused on integrating biology, computation, and contemporary design sensibilities. Following her cum laude double major in architecture from Rice University, she went on to graduate work at Southern California Institute of Architecture, where she got her master's in architecture and the Alpha Rho Chi Medal. Amber is currently an assistant professor for the School of Architecture here at Syracuse University, where she teaches both foundation studios and representation courses focused on expanding the capacity of digital media in architecture. Amber, take it away.
Thank you. And thank you all for coming. I'm looking forward to sharing the research I've been doing with my students. Hopefully it will broaden your understanding of what I consider a responsive environment. I've titled my presentation Mediated Environments, but I'm going to borrow the definition for mediated environments from the book Interactive Architecture, which was written by Michael Fox and Miles Kemp. And here they talk about mediated environments not just as how media can be integrated into our built environments, but actually as a kind of mediation. So what can we do with the technology we have now to make our built environments better? So I'm going to present this in three phases. One, what does it mean for media to make our spaces more interactive, more responsive in that manner? What does it mean for media to make our spaces more immersive? How can we actually use media as a space that we can occupy? And then what does that mean for architecture in the future? So then we'll look into what does it mean for media to act both interactively and immersively. So I'm going to show you mostly work that my students have done in this last spring. The semester was divided into two parts. The first half of the semester talked about media that manipulated our built environment quite directly. And you'll see how that works out through interactive prototypes. And then the second half was, what if we consider media as a material? So as architects, we're always talking about glass, we're talking about brick and concrete. What if we considered media as a material that we could actually build with? And what would it mean to occupy space of media? So first I'm going to introduce you to the interactive prototypes. Playing it there. Okay, great. All right, so the students were asked to actually physically design and fabricate prototypes that were machines that would take in outside sensor technology and then operate these machines. So you can see that the students actually had to physically manufacture the work, as well as design in the computer the models that were the precursor for the work that they were fabricating. And then they're going to use these microprocessors called Arduinos in order to control them. So here you see one of the machines, the little thing in the red up there, that's the Arduino board. It's like a little hard drive for your computer. And all of those wires are then connecting into the breadboard. And then ultimately that goes into the computer, where this microprocessor is controlled through a 3D modeling Rhino, which is using a visual programming language called Grasshopper, and then going back and forth between them using something called Firefly. Now that's a lot of animals. But ultimately, the work was to make these interactive devices that are using things like light and humidity and sound as drivers for the design process. So to add to that, these things were integrated into their studio work. So I teach media class as kind of a sidebar to their studio work, but in this case, the students were specifically asked to design the machines for biomes across the globe. So the machines were intended to address the Anthropocene era, which is the era in which we as humans have had a negative impact on the way that the environment works. So these machines are intended to address bio conditions and look at how they can mediate that. So this one in particular is actually using the condensate in the air. It's designed for the savanna. And as the water, so as water is condensating on the surface, then it starts to lengthen and then drop that water into a cavity down below. And so you can see in this model that the, that the model is actually working in 3 different phases. Like you can see the actual physical prototype is active. Then over here in the bottom right-hand corner, you can see the digital model that's actually active as well. And then, of course, here you see where they're speculating on how it would actually be applied into the biome of the savanna. Now, this is a condition that we are maybe more familiar with in the savanna. Now, the students are being a little bit cheeky by installing their prototype on Frank Lloyd Wright's Falling Water, but this particular machine addresses snow. In particular, it's using a translucent and colorful glass ceiling system, and then measuring the light levels below so that when it gets both cold and dark, it recognizes that it's got a snow load on it, and then flings the snow off, so clearing the floor of the ceiling. And of course, it has a decorative aspect as well. Now, some other students started to not just question like how this might be relevant to a particular biome, but actually looking at like sort of mischievous ways that this could reconsider how we engage spatial conditions, things that we already know. So you'll see that this prototype here responds by intensifying the action that's placed on it. So as they push on the surface, the thing starts to pull away. As they pull on the surface, the thing reacts by growing towards you. And it's creating these little gaps in the panels between. So you can see maybe in between those little furry things, there's actually openings that are created. Now the students decided to take this a step further at that 3rd scale where they're looking at like how would this change the environment. They're looking at like, well, this could be the way that we have doors in the future. This could be the way that we consider both skylights and windows and even furniture. Now, the second half of the semester asked them to consider what is it like to occupy media. Now, if you think about it already, media occupies a great deal of your built environment. So how many people are like used to having the meeting where like half the time everybody's on the phone, right? Like, but right now our relationship to media is generally like between us and the screen. So we had a conversation about what does that mean to our built environment, and the students came back with varying levels of responses. Now, one question was, if you've ever been to an architectural presentation, they tend to be very static. We pin up our work on boards. We still rely heavily on drawings, which will never go away. And they tend to be a kind of live presentation. But our lives are filled with things like YouTube videos and very short snippets of information delivered to us rather quickly. So one of the first things the students did was question whether or not that was the way to present, okay, that's not playing sound. I don't know. Okay, it's okay. Whether that was the right way to present an architectural design at this point, or whether we had to tell more of an immersive story about what we're doing. So what you're seeing now are clippets talking about the environmental factor, which this particular interactive prototype was responding to. It's talking about the drought across the plains and like what that's meant in terms of global change. So here you see the farmer talking about the drought and the fact that they're pumping tons and tons of water out of the aquifers, more than is being reconserved into it. So he has designed a prototype of a machine that uses technology that we've had for a while called a moisturizing vaporator. And in a second, you'll see a little clippet of the machine that he designed and how it works. And so there's a kind of bellows that moves up and down that's triggered by a humidity sensor that then allows for condensate to be captured and then translated into through piped to the plants through a kind of system underneath the ground as opposed to irrigation from up above. This guy's telling you that you don't need to worry about the environment. What you need to worry about is our place in it. And now you'll see the drawings and work that the student was doing to talk about their presentation. So here we're moving through in animation. These are solar-powered panels that are driving the energy for the system. These like pylon sort of things that you see in the field are the actual moisture evaporators. They look like giant columns. This is a site plan. So all of these drawings are typically just sort of penned up in a traditional architectural representation. But the student is trying to use media as a way of immersing us through the storytelling device of like, this is my project, this is my design, this is how it will work. So this is the interactive prototype at work. You'll see a bagged soil in a second. And then this is showing you like the Arduino device driven by a humidity sensor that's then ultimately pumping the water into the plant. Now, another way of being more immersive with media is to borrow the poor man's Oculus Rift. So I don't know if you guys are familiar with this. This is a Google Cardboard. Anybody know? Yeah? Okay, cool. Okay, so what you do is you take your smartphone, you start to play the video, you put the video in your smartphone in here, and now you've got 4 minutes Oculus Rift, right? You can buy one of these for $5 off the internet or make your own. There's templates for the laser cut file. So if we see it in action, it looks something like this.
So you hold this up and look inside. Let us know what you see. All right. Whoa, whoa. Whoa. Whoa, okay, this is negative 101. What? I'm in Paris. Oh, hello there.
Okay, so obviously somewhat immersive. So the students found 2 ways of embracing that technology as a way of both like informing their design work and also representing their design work. So this is called a Photosphere. It's you can actually do this with your phone. I did this one in a space in Buffalo, New York. And what you can do, and I'm going to demonstrate it here, maybe. So I'm going to demonstrate it here because you can't see it through the Google Cardboard device, but I can actually manipulate my space, my view of the space, using the mouse here. And it's funny because that poor guy, he showed up twice, and both times he's looking at his phone. But if you were actually looking at the photosphere in your, oh wait, you guys didn't see it.
Mm-hmm.
Sorry. Escape. No?
Can you drag it over to the...
Drag it over.
Yeah, there it is.
All right. No, I have no control over it, though.
Do you want some? Mouse for a second.
Oh, you did?
Yeah. Just there it is.
Oh, thank you. Like, I teach media, but I always say don't put your fax machines, copiers, or projectors. There you go. Okay, here we go. That's better. Okay, so I'm actually kind of sadly manipulating my way around this thing. So as I turn my head, like I can actually change which part of the project I'm looking at. So maybe this will be better not on that projector. But the cool thing is that if you look at the photosphere in your Google Cardboard device, the accelerometer in your phone actually knows which direction you're looking. And so as you're looking at the environment, as you're turning your head, you're actually turning the view that you see in a virtual environment. Okay. Get my mouse back. Yay, okay. Now, some of the students took that a little bit step further. and then learned how to make animations using spherical cameras, so that in that space, like, we can actually kind of 3D occupy the space that they designed. So it's going to look funny to you because the Google Cardboard device obviously has different lens links that you're supposed to be seeing it through. But what you'll see is sort of like how the 3D space is split into two, so that you're really sort of seeing it from two different views. So these are the same students who made the furry wall before. And you'll see how, in a minute, how they're showing the space actually operating here as well. So we're actually occupying the space as it operates. So watch the table and the wall and the ceiling. You can see that they're starting to open up in a similar fashion to what they showed in their speculative rendering before. Okay, so what does that mean about what we're going to do in the future? That all seems very, very fun, right? I think it's going to be more fun, but it's also going to challenge, like, what do we think of as our real environment, which is virtual, and what's the space between those two things. So this is a competition entry that I did with a couple of my colleagues for a competition that was sponsored by Storefront for Art and Architecture in New York City, and it was for a pavilion outside of the new museum. So the competition asked for a new space for assembly and public address, and we designed something called a digital soapbox. So here you see the pavilion in front of the new museum. An experience begins with this uninformed passerby walking into the big screen you see on the left-hand side. And so that's a static image of what the view would be beyond the pavilion, but you already start to recognize that it's not exactly the view that you would actually see. Inside of the pavilion is a projection room and an assembly space where you could watch the action happening later on. And then over here on the far right of this lower left-hand side, you'll see that there are actually embedded virtual reality viewers. So you can walk up to the wall, and it's essentially like putting your eyes to this thing, and you would see like the augmented reality device in 3D. The last step is then to go to the headset kiosk and get your own Google Cardboard, and then you would go on a scavenger hunt through the city. And what you'd be looking for is a series of QR codes which you would scan with your phone and then insert into the Google Cardboard device, and you would recognize the environment that you were in as being augmented. So there would be this moment where you would look at the environment that you're in, then start the Google Cardboard device, and essentially see something that isn't quite what's actually there. So you can imagine people doing a whole lot of this, right? And this brings me full circle to what Bess was talking about earlier. What does this mean in terms of what the COE is doing, and how does this relate back into environmental systems? So Bess and I and Lauren Covington in the back and a few other collaborators are looking for a way of manifesting our environments in a way that can be virtual and tangible. So things like energy are hard for us to describe in a way that's interactive. We tend to use a lot of graphs and a lot of color pictures that have pixels on them. But we are doing a piece of work that's funded by the COE here in collaboration with the Museum of Science and Technology, which is trying to look for a way to make research that is interactive, visualizes, and simulates so that both designers can learn from the process, but also, more importantly, to kind of bring an awareness to a larger community about what it means to make decisions about things like dynamic facades and how that affects a user both at the urban level and at the building level. So it's going to integrate both a physical model, a digital projection on the physical model, and then ultimately, of course, virtual reality through either Google Cardboard or Oculus Rift. So you can see that it's a work in progress. We've modeled the city of Syracuse, and we are working with a program called Unity 3D as a way of occupying that digital space in a way that we're familiar with through because of video games. But then ultimately, we're trying to integrate into that some kind of tangible way of describing what you see here, which is a kind of heat map of solar game, in such a way that it's tangible and interactive. So this would encourage people to be not only just aware, but start to manipulate their environments, because they could be in that space virtually, in much the same way that we saw it working in Bess's prototypes in the lab upstairs. So hopefully that gives you a broader scope of what responsive environments could be. So
that was great presentations from all three. So if you'll all come back up here, it will open up the floor for questions. So who has questions?
This picture here, what you presented, very nice.
Thank you. Well, this is a holdover from a description I was trying to make about the relationship between architecture and art and science. So it's like kind of three-strand DNA in plan view, believe it or not. And so the idea is that there's no such thing as three-strand DNA, by the way. It's something I just try to imagine as a way of tying together technology and science and art, which is where I feel like architecture really lies. So it's how I was thinking.
It's sort of related to my question. It's stimulating. I think thank you very much for the stimulating presentations. I'm always thinking about the calculation, simulation, how can we actually model the physical systems from material level, micro scale, to urban level. So we're talking about very different scales. So my thought is about is there a unified model that can cut across this different scale? And so what is your, in supporting your visualization, so interactions and users, what is your understanding of current state of such a model? Do you have to get different pieces of the things together, go at a material level, one model, get a building, a different model, urban scale, another model? Any idea whether any work in trying to develop this a unified modeling system in support of this kind of integrative, interactive, immersive environments?
Oh, quickly, so that's a great question. I think one of the things we're working through right now is finding the work that does span across these scales, which differs very much for whether we're modeling it in terms of energy performance. So even within the modeling for EDS, there's still a struggle with the workflow when you want to understand the glazing performance and then link that to even just the room scale. The workflow between those two scales is still tricky. I think where it becomes more successful in terms of maybe translating across scales is when we look at these other gaming environments like Unity 3D, where you can quickly kind of render and experience multiple frames of view very quickly. But and that's because of these gaming engines, because it's part of that interactive experience. But at the same time, those don't necessarily incorporate the kind of energy feedback that we're interested in. So, which is a large reason why we're also looking into these other gaming engines as vehicles for exploring these multi-scalar energy flows too. So, I don't know.
Yeah, I think it really has to do with the question of what you're trying to simulate.
Yeah.
Is the biggest sort of thing, because you, in order to make things computationally expedient, you need to usually operate under a set of assumptions that eliminate some things that you're not modeling in order to focus on the things that you are, because even those few things can be very complex. So in terms of daylighting, even just modeling complex scattering through a facade is complex enough that you want to shave away a lot of it. And by other things, I mean, like, let's say airflow in a room, and how the airflow with computational fluid dynamics will be very useful in terms of looking at how heat might be moving around with an off-balance mean radiant temperature due to some kind of daylight. So I think everything's interacting, so the need for an integrated model is important. But it really, it usually comes down to, you don't start from let's model everything and far away. You start with what are the few things that we do need to model. So, I mean, I think it's a labor intensity and computational cost kind of issue as to why things are not always fully integrated. Now, as far as work that people are doing, like there is new work at Case looking at this question of how do we make more integrated models. So, for instance, another system that we work on, IC Solar, which is the integrated concentrated solar facade, which you can see, maybe see, in the high bay of this building. It's a large double cavity curtain wall with concentrating solar modules inside, which have frontal lenses and concentrate on a high frequency solar cell. So you have a lot of heat gain into that double cavity space. So not only do you need to model daylighting through that, model any electrical photon to electron conversion that you're making, but then also model the airflow in that cavity to understand how you're going to heat or overheat your model. So for that reason, we need to start addressing more interrelations between physics. And so we start developing more models that bring all that together. I can tell you that there are a series of equations, like they're collections of equations that are meant to capture all those different physics. And that's not even talking about what are the other interactions that happen with how people interact with them. That's really just a physics model. So yeah, I mean, I think the need for an integrated model is important, but it's recreating the world at some point.
I think you're very familiar, of course, with how we're trying to figure out how to get energy modeling that you're familiar with into this kind of modeling that's more virtual reality and gaming. So how do we get those two systems to talk to each other? How do we figure out a way to take numbers and translate that into visual information in an interactive way? I think we're the ones who are designing those systems right now, and such a thing doesn't exist. But there's a lot of development on singular systems, and it's just a matter for us to determine how to get them to talk to each other.
Is that question from your side? The Arduinos that you guys were using doesn't seem natural that architectural students are using and programming Arduinos. Is that what's going on there? Or
yeah, those are architecture students, yes. The hardest thing for us to do is not the programming, but the kind of, we need more engineers to come over. So help us figure out how to make the actual machines that are operated so we can get the signals going, but we don't always do a great job making everything move. We're really good at the static stuff. So anybody wants to volunteer, I'd like to teach again.
Folks interacted with Ed Lipson in the physics department. So there's a connection that we have to make. He's somebody you've been after. So it's been a while since I've been to the most. One of my favorite things there was something that has been there for decades, and I'm wondering if it's still there. There's a video that was probably made in the 60s. I think it's called The Powers of 10. It goes from a galaxy to there's a picnic, and then there's down to an atomic level. Is that still there?
That must be a rite of passage to watch that video, because I haven't seen it the most, but I've certainly seen it. I don't know if it's still there, though. I don't know.
Yeah.
Lauren, you know?
What's that? Not at the moment.
That was actually by the Eames studio.
Yeah.
That's quite new.
So I think this goes back to Jensen's thing about exploring scale, so that you're at the urban scale and the building scale and the personal scale and the material scale. I think there's an opportunity there for a mediated environment to help individuals understand energy at these different scales. So is that part of the scope of energy in the city?
Absolutely.
to be able to explore at these different scales.
Mm-hmm. Yeah, and really for people to understand what their own personal choice is and how they're, well, to understand that we all have very different preferences for comfort and the way we understand and perceive our environments, but then also to understand that our personal choices will affect not just our own personal space, but actually can have implications at much larger scales. So trying to figure out ways to visualize that that's based on, real data, weather data, sensor data that's coming from this building, that's coming from the city itself. So all trying to merge those different scales so that we really create stronger connections in terms of how we understand our place in the built environment in terms of these ambient flows.
There's a question in the back first.
To piggyback on Ed's question, I'd also ask about to what degree are you leveraging georeferencing and utilizing geographical information systems as a platform and a linking mechanism to take advantage of those different scales that Ed was talking about. Mm-hmm. And also I was curious if you're working with the urban planning profession in any way, like a leader, local governments, to really try to see how this could be applied and put into place. There's all kinds of groups nationally and internationally that are leaders in similar models, and that would also be helpful.
Mm-hmm. Great questions. We're just starting conversations with someone who in Syracuse, who is leading a lot of the work in GIS. So starting to tap into the resources that he's been using and he's been teaching to incorporate some of that geographic information into these models. And that's something that we've been working on with Professor Jensen Zhang and kind of projecting even sort of beyond what this more immediate installation might be and how we can expand those models to incorporate all of that information that we might not necessarily see in our immediate environment, but it exists. And as far as working with local government, that's something that we had started a conversation about last year, just specifically within the city of Syracuse. So it's something that we've started these conversations about, but it's again a really important, I think, component to the work as we do start to expand the audience and really explore these methods and these models in more public spaces and more public environments that we can really, like Amber was saying, really invite the community and participate in that decision-making process.
You might want to check with the American Planning Association.
It seems like both Jensen and Ed would like want you to get a Nobel Prize for coming up with the universal theory of architecture. That said, I've seen some papers, different languages, presentations with it, trying to address some of the issues we're struggling with. What really happens in the real world by incorporating some fuzzy logic into some of the interactions you're projecting. I don't know if you have any plan for it, have you studied some of those? Unfortunately, the presentations I've heard were translations from Chinese and Korean, so I don't have all the details. But it looked very interesting.
Mm-hmm. Incorporating fuzzy logic into the
Especially they're looking at real schools, children at different grades, mm-hmm. how they interact with their environment. They program that into mm-hmm. the built environment. Mm-hmm.
Yeah, it's something that we've certainly looked at a little while ago, how to incorporate fuzzy logic into the control algorithms for how these systems behave, specifically with the EDDS simulations. But it is something that it sort of remains an open door. You can fight those methods to certainly be incorporated. It just hasn't been on the immediate radar just yet.
Brandon, from a perspective on the thin films, so it seems like you've selected one kind of material. How adaptive is that to new materials that you might be able to develop with some material scientists? Can you kind of modify the models to accept those new properties?
Yeah, absolutely. And that's what some of the early modeling we did was actually defined in such a way that was generic enough that it was applicable to EDDS as well as some other systems. So yeah, most of the modeling processes are fairly adaptable in terms of what kind you feed it in a kind of geometry, and you give it material properties, and you can sort of simulate the scattering that happens. But that also sort of basically, I sort of heard your question the wrong way at first, which was the adaptability of that material specifically. We're not sort of material agnostic, so we're not committed to solving the problem with specifically graphene-based materials, although there's a lot of advantages. But so I would say you can, for graphene oxide, you can actually attach other things to it. So you can functionalize it with a number of other molecules to change its properties, to adapt how that performs. So that's one we're interested in, is actually modifying material properties.
So I'm going to suggest that we adjourn to the 5th floor, where we've had this terrific presentation today, but there's a lab where you can experience some of the things that have been presented. Our usual format in an R&T forum is we have a networking time with refreshments out in the hall. We're going to move those refreshments up to the 5th floor. So I encourage everybody to have this experience of going to the lab.
Great.
In the meantime, I want to thank Chetna for moderating and the panelists for their I want to urge everyone, this just will have whet your appetite for what you're about to see in the lab. So, up to the 5th floor, the lab I'm going to go to is room 502. So it's the